0 divided by square root of omega 0 square minus omega 1 square plus gamma square omega 1. Suppose this is question number. You know, the amplitude, displacement amplitude of a forced vibration is, we can say the amplitude of a forced vibration is given by equation number 1. Or you can give equation number according to your book, according to your notebook. Suppose it was 14, then you can start from 15 as you like. So you will see that here amplitude depends upon, you will see that omega 0. We can say that omega 0 is angular frequency, it is constant, then omega 1 and gamma. And this. Now we will consider different cases. Case 1, that low driving frequency. At low driving frequency, what will happen? Well, the frequency is very low. In that case, we can say that omega 1 is less than omega 0. If omega 1 is less than omega 0, then we can neglect omega 1 square with respect to omega 0 square. Again, your gamma square, omega 1 square will be negligible in comparison to omega 0 square. So we can say that this omega 1 square will be neglected. And here also gamma square, omega 1 square will be neglected with respect to omega 0 squares. So we can write this as A equal to F0 divided by omega 0 square. So we can write this as F0 by M. This is your K by M. So we can write capital F0 by K. So from this we can say at low driving frequency, all of you listen carefully, at low driving frequency, displacement amplitude of a forced oscillation depends upon the driving force F0 and the spring constant K. What is independent of? What is independent of? The mass of the oscillator, gamma, and the driving frequency omega 1. So it does not depend upon this thing. Omega 1, mass, and damping. Okay. Now we will consider case 2 at a high driving frequency. What will be the amplitude? At a high driving frequency, when omega 1 is greater than omega 0, this is the case of, this is low driving, this is high driving frequency. So this implies omega 1 square will be greater than omega 0 square, or you can say that omega 0 square will be negligible in comparison to omega 1 square. Hence, we can write amplitude equal to F0 divided by omega 1 fourth plus gamma square omega 1 square square. So we can write this is M equal to F0 divided by omega 1 square. Because when the damping is small, in that case gamma square omega 1 square will be less than or negligible in comparison to omega 1 to the power 4. So in that case we can write amplitude equal to this one. So we can write this as F0 divided by M omega 1 square. So now you see, because we know that small f0 equal to capital F0 divided by M. So you will see that in case of a low driving frequency, the amplitude depends upon F0 and spring constant, where it is independent of M, gamma and omega. But in case of a high driving frequency, it depends upon M and omega 1 square. So we can say that at a high driving frequency, A is directly proportional to or inversely proportional to mass, as well as inversely proportional to omega 1 square. So we can say that the amplitude continuously decreases with the frequency omega 1. As frequency increases, frequency means frequency of a driving force will increase, the amplitude will decrease. So the amplitude continuously decreases with the frequency omega 1 of the external periodic force. Again also, amplitude depends upon mass, it is inversely proportional. Now we will consider the case 3, that is the case of resonance. When omega 1 equal to omega 0, that is the case of amplitude resonance. Because you will see that in that expression, if you have written that equation number 1, then you will see that when omega 1 equal to omega 0, the amplitude becomes maximum. And we will get the expression for amplitude A equal to F0 divided by omega 0 square minus omega 1 square plus gamma square omega square root. This will be 0. Then we will get F0 divided by gamma omega 1 or F0 by gamma omega 1. Sorry, omega 1 or omega 0, because we have considered omega. So from this we can write this as F0 divided by m gamma omega 1. So you will see that in case of low driving frequency, the amplitude does not depend upon m gamma omega 1. In case of a high driving frequency, it depends upon m and omega 1. In case of resonance, it depends upon all the three parameters: mass of the oscillator, damping, as well as the frequency of the external periodic force. And what will be the value of a maximum resonance? Amplitude that we can write A maximum will be F0 divided by m gamma omega 1 or omega 0 as it is. This is the maximum amplitude of maximum value of amplitude is called amplitude resonance, denoted by A. So from this we can say that the amplitude is inversely proportional to damping. Maximum amplitude is inversely proportional to the damping. So from this we can write or give the conclusion: smaller the damping coefficient, larger is the amplitude. For large damping, maximum amplitude is small. Now if we say that theoretically, not practically, it is not possible. If gamma equal to 0, then your AM will be equal to when gamma tends to 0, but practically it is not possible. That means in every system there is some damping. Already we have discussed about 3 damped oscillation. Even if without applying any external periodic force, there is some damping. That is due to that friction or radiation, etc. That is why experimentally gamma is not equal to 0. But theoretically, if you take gamma equal to 0, then a maximum amplitude will be infinity. Then comes to velocity resonance. You know that in case of a forced oscillator, your x equal to F0 divided by omega 0 square minus omega 1 square, gamma square omega 1 square to sine omega 1 t minus phi. This is the amplitude. This method of a forced oscillation, where we have applied F equal to F0 sine omega t. And we know F0 equal to capital F0 by m, omega 0 square equal to k by m, gamma equal to p by m. And phi 1 equal to tan inverse gamma omega 1 by omega 0 square minus omega 0. Now, so velocity we can write, velocity will be dx by dt. So that will be F0 omega 1 divided by omega 0 square minus gamma 1 square plus gamma square omega 1 square, square root of this into cos omega 1t minus phi. Now we know that the maximum value of a cos factor, cos term equal to 1. So at that time you will get maximum value of velocity, which is known as velocity amplitude. So this will be f0 divided by omega 0 square minus omega 1 square plus gamma square omega 1 square. This is the maximum value. This is the velocity amplitude. Now similarly at a low driving frequency we will consider when omega 1 is very less than omega 0, in that case Vm will be f0 nearly equal to, we can say that f0 divided by omega 0 square gamma 1. Sorry, here will be gamma 1. So we will get f0 omega 1 by m omega 0 square f0 omega 1 by 2. So in this case that velocity amplitude mainly depends upon the spring constant K. And that omega 1. Similarly, for other cases, you can discuss at a high driving frequency that omega 1 will be greater than omega 0. So we can neglect that omega 0 square with respect to omega 1 square, and you will find the expression. Then what is the difference between amplitude resonance and velocity resonance? The book you will see, we have written, but we have made one table. In that table, we have shown what is the difference between velocity, amplitude resonance. Amplitude resonance is also known as displacement resonance. Similarly, velocity resonance is also known as energy resonance, because at the maximum, when the velocity become maximum for us at that frequency, we have got the energy to maximum. So amplitude, in case of amplitude resonance, if you make a comparison, in the book it is given, you will note down all the points from the book. Here I am briefly discussing that velocity resonance and amplitude resonance. In case of amplitude resonance, the amplitude of a displacement of forced oscillator is maximum. Amplitude of a velocity of the forced oscillator is maximum. First point, amplitude is maximum, your velocity is maximum. Second point, at amplitude resonance, the potential energy of the forced oscillator becomes maximum, where at velocity resonance, the kinetic energy of the forced oscillator becomes maximum. At amplitude resonance, the displacement lags behind the driving force by pi by 2, whereas at velocity resonance, the velocity is always in phase with driving frequency. And some other points are given in the book. We have given 6 points. You can read the book, 6 or 7 points also. Then we will discuss about acceleration amplitude. The same type of explanation will be acceleration amplitude. Already we know that f equal to f0 sin omega 1t and x equal to square root of f0 divided by omega 0 square minus omega 1 square plus gamma square omega 1 square into sin omega 1t minus of pi 1. Then you find the expression for velocity. Then you find the expression for amplitude. Sorry, acceleration. This is the acceleration. That is a equal to t square x by dt square. I think all of you will be able to do. So this we can write minus f0 omega 1 square divided by omega 0 square minus omega 1 square plus gamma square omega 1 square. I am sent a study at here, but all of you listen carefully like this. So you will see that the acceleration becomes maximum when the sine function will be maximum, and we know that maximum value of a sine function is equal to 1. So we can write the amplitude of the maximum amplitude of acceleration equal to f0 omega 1 square divided by square root of the speed. Okay. Because we have taken the amplitude, maximum amplitude. Or maximum acceleration is known as acceleration amplitude. Again, we will see that what happens at a high driving frequency, at low driving frequency, and its value. We can discuss these things. It is really. So after knowing the display amplitude, velocity, and acceleration of the first oscillator, then we have to calculate what is the power supplied to the first oscillator. In order to calculate the power supplied to a forced oscillator, let us consider a forced oscillator which is impressed by an external periodic force F. Suppose it displaces through a distance x, then the work done by the driving frequency, driving frequency means that is the external periodic force to produce displacement x. We can say that the work done equal to, we can write force into displacement. So we know the expression for force. We will substitute here. Again, displacement, that dx by dt. Already we know these things because your f equal to f0 sine omega 1t. So after substituting these things, we can write the rate of doing work is the instantaneous power. So we can write power equal to force into velocity, that dx by dt. Now we substitute the value of f, that is f0 sine omega 1t, and dx by dt already we have calculated. So substituting these values, we can write this as f0 sine omega 1t into f0 omega 1 divided by omega 0 square minus omega 1 square square plus gamma square omega 1 square to cos omega 1t minus 5. Only substituting these values and simplifying, that we can write this is sine omega 1t into cos omega 1t. So we can write f0 omega 1 divided by this omega 0 square omega 1 square. Only simple mathematics, I think all of you will be able to do. Then sine omega t cos a minus b, cos a cos b minus sine a sine b, cos a cos b plus sine a sine b. Then you multiply by that sine omega 1t, then you will get two terms. Here directly I am writing sine omega 1t cos omega 1t cos phi 1 plus sine square omega 1t into sine phi 1. I think all of you have. All of you know this expression. Now, in order to calculate the average power over a period of time, in order to calculate the average power over a period of time, we have to calculate the average values of the sine and cosine functions. In order to calculate the average power over a period of time t, we have to calculate the average values of a sine and cosine functions. Already, I think you have to remember, we have also calculated 0 to t, that 1 by t sine square omega 1t dt. This is called half. Sine square function 1, half, cos square function half, then sine function and cos function multiply. Sine omega 1t, that I can write here, that you will calculate 1 by t integration sine omega 1t cos omega 1t dt will be 0, 0 to t. I think all of you know. Already we have also calculated our function. 0 function, then we are getting half, and our function we are getting 0. Okay, I think all of you know these things. So now if we substitute these values, then we will get the P average. Because we have taken already averaging, so we will get to P average. F0 small 0 omega 1 divided by omega 0 square minus omega 1 square into half sine phi 1. Again, we know that tan phi 1, we know from the text, tan phi 1, sin phi 1 and cos phi 1. So we can substitute in these values, we will get m f0 omega 1 pi omega 0 square minus omega 1 square equal to this into half, then sine phi 1, that is gamma omega 1 divided by omega 0 square minus omega 1 square plus gamma square omega 1 square. This is the one. Okay, then we can get this value as half mf0 square gamma omega 1 square divided by omega 0 square minus omega 1 square according to your copy. You can give the equation. Everybody clear how I have calculated? I think it's only simple mathematics. You will be able to know. Maybe I have omitted 1 or 2 steps, then I think it will not be a problem for you. In the book also it is given. If I will send the study material, also it is given. So equation number I have not given. According to your copy, you can give, suppose this is your equation number A or whatever it may be. That equation number A represents the average power supplied by the driving force. Equation number A represents the average power supplied by the driving force. Driving force means within bracket also you may note down like external periodic force to the forced oscillator. This also represents the average power dissipated. The average power dissipated by a forced oscillator against a damping force, or average power absorbed by the oscillator to maintain the forced oscillation. Again, I am repeating. This also represents the average power dissipated by the forced oscillator against a damping force or average power absorbed by the forced oscillator to maintain the forced oscillation. Clear to this point? I have said one is that this is the power supplied by the driving force. Again also, this represents the average power dissipated by the forced oscillator. Again also, the average power absorbed by the oscillator to maintain the force. So I have said 3 things. For 3 things you will get same expression. So for one, I have derived that expression. For other 2 cases, all of you will try to derive. Calculate the power dissipated by a forced oscillator. Calculate the power dissipated by a forced oscillator. Finally, you will get the same expression. Similarly, also, if you will try to find the power absorption, the average power absorbed by the oscillator to maintain the forced oscillator, this is the expression. Also, you will get. So the homework is calculate the power dissipation by forced oscillator. How you will calculate? For this, you know the damping force. Then the rate of doing work against a damping force equal to damping force into velocity. To substitute the expressions of a damping force and velocity, and taking average, you will get this expression. Okay, all of you will try. It is also given in the book. How to do that?
Sir, but one doubt.
Yes.
Sir, then how is it different from the expression which we have derived? It will be same like all the calculation, everything, or is it something different?
These are not same. Final result you will get same. For this one, I have said the procedure. For second one, the power dissipated. Power dissipation means for this one we require the damping force. So you have to write the expression for damping force. Your damping force expression minus a P dx by dt, PV. So that will be minus a m gamma dx by dt. Now you substitute the value of a dx by dt. Again, the rate of doing work against this damping force, that will give the dissipation. So in that case, you will write damping force into velocity. Here you have written force into this velocity. Here it will be damping force. P prime, suppose we are saying that is the power dissipated. That we will say that the rate of doing work against the damping force, your P prime equal to damping force into velocity. Now you substitute the expression. Your damping force this one, then velocity expression. After that, you find the time average. Average sine function plus sine function. Finally, you will get the expression this one. This is the P average supplied. This is the dissipated. The expression will be same. Okay. Then we will discuss about sharpness of resonance. You try. If you have any doubt, you already I said in my classes, I am joining at least 10 to 15 minutes before. You can join. At least 5 minutes before you can ask me. There is no problem. If you have any doubt, it is given in the book. If I will send the study material, I think it is also present there. Still then, first you will try by yourself, then you will see the book and study material, etc. Now we will discuss about sharpness of resonance. Sharpness of resonance. Yeah. The sharpness of resonance, the definition we can see. Sharpness of resonance, basically, is the ratio of, or mathematically we can say that AM, maximum amplitude to amplitude. This is the definition of the sharpness of resonance. We know the expression for amplitude. Here A equal to F0 divided by omega 0 square minus omega 1 square plus gamma square omega 1 square. You know these things. Again, what will be the maximum amplitude or amplitude resonance? That from this we can write, or already we have derived AM equal to F0 divided by gamma M omega 1. When the omega 1 equal to omega 0, we will get F0 divided by gamma omega 1. Small f0 equal to capital F0 by T. Suppose this is the expression 1, 2, 3. amplitude, maximum amplitude, then sharpness of resonance. You can write this also as f0 by gamma omega 1. This one, from this. Okay. Now, we'll find the value of AM by A, that is sharpness of resonance, which we can write f0 divided by gamma omega 1 into omega 0 square minus omega 1 square. So we can write, this is okay. So we can write omega 0 square, omega 1 square. This will be we can write this as 1 plus a half omega 0 square, omega 1 square approximately. This is the approximately. So you will see that sharpness of resonance varies inversely as the square of a damping. So we can write hence smaller the damping, sharper is the resonance. Hence smaller the damping, sharper is the resonance. Okay. Then we will discuss another parameter, that is the bandwidth of resonance. Bandwidth of resonance. For this, all of you, actually, we have derived the expression for power. This question is easy. Otherwise, you give the heading, bandwidth of resonance, I will draw the figures here. Then already we have derived the expression for power. If we plot a graph, that is power versus the frequency. Frequency means frequency of external periodic force, omega 1. That is P average. Already we have derived the expression P average. Suppose this is the maximum value. P average, can say that P average, then this is the maximum value. P average max. Then we will consider this is the value of half P average max, half of the average maximum power. Okay. Here we have obtained 2 points. Suppose point 1 and 2 corresponding omega and same. Omega 1 at the point 1. This is the omega 1 at the point 2. Or in some books it is written A, B, omega 1 A minus omega 1 B. As you like. If you write, this is okay, I am writing 1 and 2. Or you could say that this is the point A, point B, 1, 2. As you like, you can write. So bandwidth of resonance is defined as bandwidth of resonance is defined as the difference in the values of a driving frequency. The difference in values of a driving frequency at which the average power observed drops to half its maximum value. Its maximum value means within a bracket you may write down resonant value. Again, I am saying, all of you have written that statement. Average bandwidth of resonance is defined as the difference in values of a driving frequency at which the average power observed drops to half its maximum value or resonant value. Again, all of you look at the figure. In the figure, it is drawn the average power versus the external periodic force frequency of external periodic force. P average versus omega 1. You see, this is the maximum value of the power at resonance, and we have plotted here. We have shown this is the half of the maximum average power of the oscillator, and corresponding points we have taken. Suppose at A1 and 2, and the values of a frequency, corresponding frequency, we have noted as omega 1 at 0.1 and omega 1 at 0.2. That means at 0.1 and 2, the average, the power of the oscillator equal to half of its maximum average power. Clear to this point? According to the definition of bandwidth of resonance, it is the difference of the frequencies. Means omega 1 2 minus omega 1 1. It is the difference of the frequencies at which the power of the oscillator is half of its maximum value. Everybody clear about the definition of bandwidth of resonance? Anybody has any doubt? It is the difference in frequencies at which the power of the oscillator is half of its maximum average power. Maximum average power. Okay. So now we know the value of P average. We know the expression for P average. So I am erasing the figure, then I can write. We know that P average equal to half. Already we have derived this expression. F0 square gamma omega 1 square divided by omega 0 square minus omega 1 square plus gamma square omega 1 square. Already we know. So what will be the maximum value? P average maximum value when omega 0 equal to omega 1. So we will get half m f0 square gamma omega 1 square divided by gamma square omega 1 square. That means that when omega 1 equal to omega 0, we will get maximum power. Now, in order to calculate the bandwidth, we have to find the frequencies at which P average equal to half of the maximum P average. So we have to write P average equal to half of P average maximum. Everybody clear this expression? This is suppose 1, 2, 3. Everybody agree with these three expressions? Then you substitute P average here, equation number 1. You can write the value of here that half into this one. M0 square gamma omega square by omega 0 square minus omega 1 square plus gamma square omega 1 square. P average, then half of P average maximum. Half of, this is the value of F0 square gamma omega square divided by gamma square omega 1 square. Everybody clear? Then from this I can write omega 0 square minus omega 1 square gamma square omega 1 square, that is equal to q gamma square omega 1 square. So we can write omega 0 square minus omega square plus or minus a gamma omega 1. So omega 0 minus omega 1 equal to plus or minus gamma omega 1 divided by omega 0 plus omega 1. This is what was our equation 4 or 5. Okay, now at resonance, what will happen? We will take omega 1 equal to omega 0. Nearly approximate equal. So in that case, we can write omega 0 minus omega 1 equal to plus or minus a half gamma omega 1. It will take approximate equal. Now, if omega 1 at 2 is greater than omega 1 at 1, according to our figure, then we can write omega 1 2 minus omega 1 is nearly equal to plus half gamma, and omega 1 1 minus omega 1, that is equal to minus a half gamma. So if you subtract, then you will get omega 1 2 minus omega 1 1. This is equal to gamma. So you will find the expression. What is this omega 1, omega 2 minus omega 1? This is the bandwidth. So we can say that the bandwidth expression is gamma. Which is equal to P by M or whatever it is. So we can say that already we know your sharpness of resonance is inversely proportional to gamma square. So if is smaller the bandwidth, sharper is the resonance. Smaller the bandwidth, sharper is the resonance. This is the physical significance of the bandwidth. Smaller the bandwidth, sharper is the resonance. Then one more factor parameter is there, that is quality factor. Quality factor Q. This is also known as a figure of merit of oscillation. This is also known as figure of merit of an oscillation. And the expression, I think all of you know that Q equal to 2 pi into average energy stored per period divided by average energy lost per period. And your Q equal to omega 0 by gamma. This is also, we can say that M omega 0 by P, like this. So your quality factor is a measure of sharpness of resonance. It's a measure of sharpness of resonance. Higher the Q value, smaller is bandwidth. Gamma less than Q high. So higher is the Q value, smaller is the gamma. Gamma means your, what is that gamma? Gamma is the bandwidth. So higher the Q value, smaller is the bandwidth. That means sharper is the tuning. Higher the Q value, smaller the bandwidth, sharper is the tuning. So from this equation we can say sharpness of resonance is directly proportional to the natural frequency of the system. And inversely proportional to the damping coefficient. Inversely proportional to the damping coefficient. Another HW I am giving that all of you derive the expression for quality factor. That Q equal to omega G by the it is given in the proof. All of you will try to derive. Already I have given another homework that derive the expression for power absorbed or dissipated of forced oscillator, and this is also one expression, but quality factor. Then another point we can note down, another HW, so that the Q value as an amplification factor at low driving frequency. At low driving frequency, this Q value is equal to amplification factor. That means at low driving frequency, you have to show that AM by A equal to Q. Nearly equal to Q. AM by A equal to Q. So this is the third HW. HW3, HW2, another HW I have. Since this tomorrow and the day after tomorrow, Saturday, Sunday are holidays, all of you will try to complete these HWs. Then application of resonance.
Sir, what was the condition for third HW? At which condition?
At low driving frequency. At low driving frequency, so that the quality factor is equal to amplification factor. Or in other words, your question will be like that. So that the displacement at a low frequency, this is the displacement at low frequency, is amplified by a factor Q. This is the original Q, sorry, amplitude. Now it is amplified by Q. Then we are getting amplitude. So displacement at low frequencies is amplified by a factor Q at displacement resonance. Means maximum value of amplitude, maximum value of amplitude equal to amplitude amplified by Q, quality factor. Then you will get maximum amplitude. This is the indirect question. Okay, with this, almost your first oscillation. First oscillation and resonance. You will see in the syllabus linear superposition principle, position of superposition of two perpendicular harmonic oscillations having same and different frequencies and phases, three damped forced oscillations, equation of motion, amplitude resonance, velocity resonance, then quality factor, sharpness of resonance, etc. Your first unit, that is the harmonic oscillations, is completed. I will send the study material today if possible. Then all of you will go through from the first class 2 up to today's class in detail. Then you make your pair notes along with that class note as well as your book. That will be helpful for your examination.